Imagine two solid cubes with exactly the same dimensions. They occupy the same volume, yet one has much more mass than the other. How can equal-sized objects contain different amounts of mass? Size alone cannot describe this difference. We need a property that connects the mass of an object with the volume it occupies. That property is density. The cubes have equal volumes, but the second cube has the greater mass. Which cube has the greater density? Make your prediction before we define the term formally. It is the second cube. When volumes are equal, fitting more mass into that same volume produces a greater density. Density means mass per unit volume. In other words, it tells you how much mass is present in each unit of volume. A high-density material has more mass for the same volume than a low-density material. Density is therefore not simply another word for heavy, and it does not merely describe how large an object is. It relates both quantities. We write the relationship as ρ equals m divided by v. The Greek letter ρ represents density, m represents mass, and capital V represents volume. Read the division as sharing the total mass across the measured volume. If mass is measured in grams and volume in cubic centimeters, density is measured in grams per cubic centimeter, written G per centimeter cubed. Consider a solid ornament with a mass of 240 grams and a volume of 80 cubic centimeters. Start with ρ equals m divided by v. Substitute the measurements. Density equals 240 grams divided by 80 cubic centimeters. The quotient is 3, so the density is 3 grams per cubic centimeter. The unit records exactly what we calculated, 3 grams of mass per cubic centimeter of volume. For a liquid, you need the mass of the liquid itself and its measured volume. Find the liquid's mass separately from anything holding it and measure the volume of liquid. Then use density equals mass of liquid divided by volume of liquid. The container is part of the practical method, but its mass must not be treated as though it belongs to the liquid. A regularly shaped solid follows the same equation, but its volume is obtained from its regular shape. Measure the solid's mass, calculate its volume from the measured dimensions, and then divide mass by volume. Notice the structure. The density equation never changes. What changes is how you obtain a reliable value for the volume before making the calculation. Now picture a stone that sinks, but has an uneven surface. Its dimensions do not fit a regular shape calculation. How could you find its volume? Submerge it in a liquid and use displacement. The sinking solid raises the liquid level, and that increase gives the solid's volume. In a before and after diagram, first locate the initial liquid volume. Then inspect the second level with the irregular solid completely submerged. The solid has displaced liquid, so the level rises. Subtract the initial reading from the final reading. Volume of the solid equals final liquid volume minus initial liquid volume. The change between the two readings is the quantity you need. Suppose the liquid level begins at 50 cubic centimeters and rises to 70 cubic centimeters when a 60-gram stone is submerged. Its volume is 70 minus 50, which equals 20 cubic centimeters. Now apply ρ equals m divided by v. Density equals 60 grams divided by 20 cubic centimeters, giving 3 grams per cubic centimeter. Each reading has a distinct role.
A tempting idea is that the heavier object must always be denser. Test that claim against the equation. Density is mass divided by volume, so mass alone is not enough. A greater mass might be spread across a much greater volume. Only when the volumes are equal can the heavier object be identified as denser from mass alone. Otherwise, calculate or compare both mass and volume.
Density data can also tell you whether an object floats. Compare the object's density with the liquid's density. If the object has a lower density than the liquid, the object floats. This is a comparison, not a judgment based only on whether the object feels heavy. You need the densities of the object and the liquid. An object has a mass of 90 grams and a volume of 120 cubic centimeters. Calculate its density, then decide how you would use a supplied liquid density. Rho equals 90 divided by 120, so the object's density is 0.75 grams per cubic centimeter. If the liquid's density is greater than 0.75 grams per cubic centimeter, the object floats. The calculation comes first. The comparison completes the decision. Here is the supplement extension. The same comparison works for two liquids, provided they do not mix. The less dense liquid floats on the denser liquid. Their masses alone do not determine the order, because density still relates mass to volume. Compare the two density values, then place the lower density liquid above the higher density liquid. Two non-mixing liquids have densities of 0.8 and 1.1 grams per cubic centimeter. Predict their vertical order. Which liquid forms the upper layer? The liquid at 0.8 grams per cubic centimeter is less dense, so it floats above the liquid at 1.1 grams per cubic centimeter. Match each material to its method. How do you obtain mass and volume for a liquid, a regular solid, and a sinking irregular solid? Pause and retrieve all three. For the liquid, find the liquid's mass and measure its volume. For the regular solid, measure mass and calculate volume from the shape. For the irregular solid, measure mass and find volume by liquid displacement. Every route finishes with rho equals m divided by v. Transfer the model to a fresh object. Obtain its mass, obtain its volume by the method suited to its shape or material, and calculate density. If floating is involved, compare its density with the liquid's density. At supplement level, use the same comparison to order non-mixing liquids. Your compact self-check is this: mass divided by volume gives density. Lower density floats above higher density when the stated conditions apply.